So, this is the portion where I remind you how extremely and excessively important it is to have units with your answers. Where appropriate, we'll randomly get to some values that don't have units, but we'll have a great big discussion about what those values mean and when we get there, and it'll make a little more sense when you go to label it. So, units are important because they give meaning to numbers. And, right, of course, I have found a meme that goes with it. So, right, the question is for a lot. It depends on the context. $4? No. For murders? Yeah. I mean, hopefully you think that that would be a lot of murders. So, the labeling of the values that you report is super important and therefore super required. There are two common systems of units. The two systems are the English system and SI system, which is the um, international system of units. Now, the English system is only common because we happen to be in the United States. There are not too many countries that use this system. So, SI units are what we will rely on in our class because we're going to match the scientific community here. And you may have seen some of these units before. However, let's take a look at them. I've got a table here with the base units because the way that SI units work is that we will have a base that tells us if we're measuring length, mass, time, temperature, and then we'll have a prefix that tells us how big that is. So contrast this to the English system where we have something like inches, feet, and miles, where it's only ingrained experience that lets you know that an inch is smaller than a foot and a foot is smaller than a mile. And we have conversion factors that let us go between all of those different values. In the SI system, the base unit of length is a meter, and then we use the prefix to say if it's small or big. Now, you need a number to go with this to set the magnitude, but let's just take a quick look at what is maybe a good example, which is length. Let's do 1 meter of length for a base unit. The prefix, if I use the prefix centi, which is 10 to the minus 2, a centimeter would be small. So 1 centimeter versus 1 meter, a centimeter is smaller. Kilo is a prefix that means 10 to the third. So 1 meter versus 1 kilometer, or we end up just saying kilometer, or I do. I don't know the proper way to pronounce that, but that's just what we're going to go with. A kilometer is big compared to a meter. So these prefixes, you will see, you should be able to use these. You will see them on the equation sheet for this class, but get familiar with these and how to convert in between these. And we'll have some examples to look at as well. So the prefixes that we have listed go from femto, which is 10 to the minus 15, which is super small, all the way up to tera, which is 10 to the 12th, which is extremely large. And I've marked the base unit here. So it's not explicitly listed as a line in this table, but in between deci and kilo, which is listed here, right? We don't have exactly every prefix in this table, just by the way, in case you're looking at other tables and see some things listed that are not in here. The base, which would be 10 to the 0, because 10 to the 0 is 1. So that's our base unit would be right here where I've marked it. Now, we should also talk about some derived units because there are important units that we will use that don't show up in our base unit. So we don't have a base unit for something like volume or speed. So, or density even. So the derived units, there are many more that exist than this, but let's talk about this one. The speed derived unit is meters per second. The volume derived unit is meters cubed. And the density derived unit is kilograms per meter cubed, right? Because density is mass divided by volume. Now, you will also see different versions of these derived units that include the prefixes. So, kilometers per second, for example. You might see cubic centimeters for volume, or grams per milliliter for density. And those are all still derived units that work with our international system. Of these units, some of them are intensive properties and some of them are extensive properties. So density is an example of an intensive property, and what that means is that it is not dependent on the amount of substance that you have. So if I have a 2-gram sample of iron and I have a 5-gram sample of iron, they would both have the same density because there's only one density value for iron. Now, mass is an example of an extensive property. It depends on how much you have. My smaller sample of iron has a different mass than my larger sample of iron. So let's look at a practice problem with this. So you've been given a ring that is platinum. I've got quotes around this because someone's telling you it's platinum, but you take a look at it and it doesn't feel heavy enough. The ring has a mass of 3.15 grams and a volume of 0.233 cubic centimeters. Platinum has a density of 21.4 grams per cubic centimeter. And our question is the ring platinum? Now, this is a good place in the video if you would like to pause and try to solve this problem on your own and then come back and look at the solutions. I highly recommend it. And hopefully that was enough time for you to pause, and welcome back. Let's look at some solutions. So I have two solutions that I want to show you. What I really want to emphasize for this class is that there is sometimes more than one perfectly correct way to solve a problem. So I'm going to show both of these here. You may like one better than the other. Great. Do whichever one makes sense to your brain. As long as it is a valid way to do the problem, I don't care if you do it that way. It just has to be a valid way to do the problem. So one solution possibility is that you could calculate the density of the ring that you have and compare it to the density of platinum. So density, the value we're given is in grams per cubic centimeter. We very nicely have a mass in grams and a volume in cubic centimeters, so we can use these numbers to calculate the density in grams per cubic centimeter, which would be 3.15 grams divided by 0.233 cubic centimeters. This gives us a value of 13.52 grams per cubic centimeter, which does not match our density given for platinum, so definitely not platinum. This may not have been an obvious setup to you. This may have been the most obvious setup to you. Either way, there's still another way that we could solve this problem. And that is, we could take the density and the volume that we have and calculate what the mass of the ring would be if it were pure platinum, and then compare it to the mass of the ring that we have. For this, there are also many ways that you could set this portion of the problem up. What I have done is set up a proportion. So a density of 21.4 grams per cubic centimeter, I'm going to set that equal to some unknown mass over 0.233 centimeters. Now, I'm going to put my 21.4 over 1, right, because I need that in order to cross multiply and solve my ratio. But this will let me find out what the mass would be if it was made of pure platinum and had the correct density given the volume. When I cross multiply, what I end up with is that the mass will be equal to 21.4 times 0.233. And after I cancel out my units, I'm left with 4.99 grams. Now, the ring that I was given has a mass of 3.15 grams, so there's no way that this ring is platinum.